So, our first coronavirus lecture for physics, and we are going to introduce a topic of conservation of momentum. So, we've learned about three kinds of mechanical energy: potential energy due to gravity. Gravitational potential energy is equal to the mass in kilograms times the gravitational acceleration of whatever planet you're on, usually Earth, times the height in meters. And so G is equal to 9.81 meters per square second. Make sure you treat that as positive. We have also spring potential energy, PES, is 1/2 times the spring constant measured in newtons per meter times the stretch or compression distance x. And then finally we have kinetic energy, 1/2 mv squared. So the law of conservation of energy, which is one of several conservation laws. There's conservation of charge and conservation of other things on there. Momentum is one of the ones we're going to be working on next. Basically just says that the total energy before an event is equal to the total energy after an event. And so you might say, well, what are events? It could be any 2 points in time that you want to look at. So you define what those 2 moments in time. So, there might be a person starting at the top of a slide and going to the bottom of a slide. And so your energy before she moves is equal to the energy after she moves. Now, law of conservation of energy always holds, but it's really hard experimentally to verify that, because friction can be involved in things too, and friction is a type of energy. Friction can do work on things, and you lose a lot of energy by friction and vibration, and so it's really tough to add it all up experimentally. So a lot of these are theoretical cases on here. So conservation of energy, I think you've all had the understanding that you have a particular roller coaster up here, and you set that roller coaster up, and I'm going to be trying to write here with my pen tablet here. And over here at the top of a roller coaster, the highest point here, we have a situation where we have all potential energy, so all PE up here at the top. Then as the roller coaster descends, we of course are picking up speed, and so we have kinetic energy, but they are still some height off of the bottom here, and so they're somewhere here in the middle. So this roller coaster here has all potential energy. Well, I'm sorry, some potential energy as well, not all. But it's got a mixture of KE and PE. And then finally, down here at the bottom, I'm going to change pen thickness here. We have a roller coaster with all KE, all potential energy down here, because all of the energy has been transferred into kinetic. And so the roller coaster is obviously moving the fastest right here. It has the final velocity, the fastest velocity down here at the bottom. And then it will begin ascending in here. And so here we have, again, a combination of kinetic energy and potential energies here. And so if you were to add all of these up, and let's say potential energy was 500 units up here at the top, then the combination here of potential and kinetic would also add up to be 500. The kinetic energy down here at the bottom would be 500 units. And then the combination of potential and kinetic here, add them all up, is, guess what? Again, 500 units. Now, the problem with that is, of course, friction. We're assuming that the track is frictionless on here, and that makes it somewhat difficult. And so the track is going to be eating up some of that energy on there. That's why the highest hill on a roller coaster is always going to be your highest hill, because that's going to give you all of the energy, and then every other hill after that's going to be lower in energy. All right? So, mathematically, what this tells you is that the total mechanical energy, which we'll abbreviate as ME for mechanical energy, is just a sum of all of the potential and all of the kinetics. And I didn't have any spring potential energy in this particular example. So the conservation of energy compares 2 moments in time, and so you have before and after. And so we can say that the initial mechanical energy is equal to the final mechanical energy. And now you get to write that out mathematically. So the initial mechanical energy is the initial potential plus the initial kinetic. And that has to equal the final potential plus the final kinetic energy and neglecting any kind of frictional forces on here. And I believe this is on your equation sheet. So this is without friction, and if you want to add friction in, then the energy at the beginning is going to be higher than the energy at the end, and so you need to add this work done by friction term on here. And of course, the work done by friction, work is just, mass times, work is just force times distance, so like the force of friction times the distance that the friction acts on. I'm sorry, I can't write really well yet. I'm going to do something to change that up while our corona closure is happening here. So this is just the work done by friction times the distance. You just substitute that in. And of course, you got to figure out the work done by friction and the distance. We'll be working with both types here. So these are your two big equations right here. So with friction, without friction is what we're going to be dealing with. All right, so sample problem time. And again, I'm sorry about the writing being so bad here, but we'll give it a shot. Got to do what you got to do. So this says, starting from rest, a child zooms down a frictionless slide from an initial height of 3 meters. What is her speed at the bottom of the slide? Assume she has a mass of 25 kilograms. And so I'm going to draw just a basic shape of a slide, and I could do better in here, but here's the girl, legs, arms, and she's going to zip down, and down here at the bottom, this is where she ends up at, just a dotted drawing. So this is the initial state right up here, and this is the final state right down here. So the way I want you to set these problems up, and what you'll be showing me every single time as you write these out, I would always start every single time with KEF plus PEF is equal to, and I'm sorry that my awesome tablet here, my pad, wants to connect these two lines whenever I do equal signs, but that's the best I can do. But that's supposed to be an equal sign. I'll try to fix it right now, but it likes to connect those. And I'm sorry, I don't know what I was saying. I don't know if I called those F or I, but they're supposed to be initials. So let me erase these. These might be F's. Anyway, it's kinetic energy initial plus final energy, potential energy initial. So these are supposed to be I's and not F's. Change the shape here again. So we got initial kinetic energy plus initial potential is equal to the, and somebody probably won't like the fact that I started with potential here, is equal to the final potential plus the final kinetic. And that's supposed to be an F plus any work done by friction. So it's frictionless slide, so that goes away. So we're ignoring that right now. So you start with this equation right here, and then you substitute what types of energy this person has. And you got to be thinking, okay, do they have kinetic energy? Do they have spring potential energy? Do they have gravitational potential energy? So in the beginning, the initial state up here, the amount of initial kinetic energy is 0 because she hasn't started moving yet. And so she does have initial potential energy. So mghi. And it's supposed to be an I, but it wanted to connect the dots because it just does. And so that has to be equal to the final potential energy at the bottom. Well, she's at the bottom of the slide, zilch, plus any kind of final kinetic energy. Well, she does have final kinetic energy. So 1/2 mv f squared. All right. So I want you to show this. I want you to show the root equation and then substitutes. Tell me that there's 0 initial. Substitute an equation in for potential energy. Now you might have both gravitational and spring potential energy as your initial one. So there might be 2 terms here. Same thing over here. You might have gravitational and spring potential energies in the final state. All right, so I've got this right here. I'm going to change out colors just because I'm already bored of what I got here. So color choice, let's go to orange, and keeping the same size. All right, so the first thing I notice right here is that the m's are going to cancel out. So you notice I didn't tell you her mass on here, which is good because it cancels out. Masses will usually cancel out unless there's spring potential energy, because spring potential energy, 1/2 kx squared, doesn't have mass in it. And you can see how it likes to connect those lines because of course it does. All right, so now we're left with G times the initial height. Well, her initial height over here is 3 meters. And I should have wrote that in here. I should have put a little line over there and said, you know, this is 3 meters high. So 3 meters for her height. And so that has to equal 1/2. Don't forget the squared. The common mistake is forgetting the squareds. So 1/2, the m is canceled, times her VF that we don't know, squared. All right, so there's our mathematical setup. I'm going to give me a pause here for just a second and bring up the calculator. All right, I got the calculator booted up here, and so let's solve this mathematically. So I need to multiply this by 2. So if I bring my 2 over, so that's 2G times 3. And a lot of you are like, well, why don't you just multiply the 2 and 3 together? Yeah, you can. You can do whatever you want. It's a free country. And so this is going to be equal to now VF squared. And I'm going to scroll this down a little bit here so we got a little bit more space. I'm going to extend. All right, so we got to take the square root. And so we're going to take the square root of 2 times G times 3. And I like how that connected it because of course it did. Why wouldn't we want to connect it? I don't know why it has to just not obey my commands, but it doesn't. So I took the square root, and this is equal to VF, your final velocity. So there, an equal sign. Alrighty. So now we just got to plug and chug this. And so I got my handy dandy calculator up and ready. So here's my calculator. I can't get it all on the screen here. It's kind of big. Oh, maybe I can. So 2 times 9.81 times 3, enter, and then take the square root to the 0.5 power. And it looks like we have a speed of 7.7 meters per second. So final speed, this is equal to, and of course it connects it, equals 7.7 meters per second. Oh, sorry, I said the button there. Meters per second. And there, ladies and gentlemen, is our final answer. All right, so I've taken some steps to hopefully be able to write better in the future. Here's our sample problem. And at this point, then, if you follow the directions on Teams, I got some sample problems I want you to work. I have posted the book right there, so you can go right to the page and right to the numbers. And I haven't done that yet, but I may end up just cutting those out and posting an image so that you can just bring up the image and do those problems. What I would like you to do is work those problems through. I would like you to go ahead and put them in Teams on a Word document, and you can use the handwriting tools like I told you before and write those out. There's 3 of them, and so I'd like you to compute those. If you have any questions, get me on email, get me on Remind, and send a message to the Teams chat. No, not the Teams chat, but the discussion area right there. And I will be available 7:30 to 8-ish, 8:30, I mean, around 8:20 is when we get out usually. So if you have any problems, let me know. Tomorrow I will post my work on these problems, or at least the answers to those problems. As a matter of fact, you know what? I'll post the answers to the book problems right along with the assignment so you can check them because they're odds. And so you can just look those right up and you'll have those. And if you want to see anything worked out, let me know and I can make a video of that. All right. Thank you very much. And let me know if you have any problems.